Thank you very much. Good morning, dear laureates, students, distinguished guests. I chose not to talk about my path to Stockholm, but rather devote my lecture to a topic that is supposed to matter to all of us. I'd like to share with you some thoughts about the future of healthcare. We often hear that big data and AI may jointly revolutionize healthcare. I would caution that AI can only be as good as the data used for its training are. And the available health data may not be good enough for establishing preventive care for two reasons. First, because their majority has been collected at a late stage of diseases that future preventive care should spot long before symptoms manifest. And second, because the sparse data collected at early stage of a disease from other individuals may not allow spotting early disease development reliably in our body. Simply because we are all different. So obviously, data sequences acquired at early pre-symptomatic stage are in need, with methods that are affordable at populational scale. These are the grand goals our team in Germany, in Hungary, and meanwhile in Hong Kong pursue. An affordable preventive care that captures severe diseases in their earliest stage of development is an overwhelming challenge that, if at all, can only be met in an international effort. That's why I triggered a global initiative, Protecting Health, because the problem to be addressed is truly global. Every year, 17 million people under the age of 70 die of, and many more lose their ability to work due to non-communicable diseases, briefly NCDs, with the four most prevalent ones being cancer, diabetes, cardiovascular, and chronic respiratory diseases. 86% of them in low and middle-income countries. Most of them are preventable by early detection. The tremendous loss of life and life quality and the loss of immense resources implied by late diagnosis of chronic conditions can only be mitigated by preventive care, which must also be affordable. Enormous challenge. Blood-based diagnostics offers a ray of hope, at least that's what we believe, thanks to a key hallmark of being alive, homeostasis, a process that keeps our organism within the range of favorable or ideal internal conditions. As a result, the molecular constituents of human blood are regulated within narrow person-specific concentration ranges around their so-called homeostatic value to maintain proper functioning of the organism. Chronic diseases systematically up or down-regulate molecules of human blood, which is actually the fundament of our hypothesis that human blood is likely to carry the molecular information needed for comprehensive screening for NCDs. Now, the question for a physicist is, of course, can physics possibly contribute to acquiring this information? More precisely, can physical technologies access a range of molecular signals responding to NCDs sensitively enough to capture them at an early stage to allow timely interventions? A closer look reveals that this question is actually incomplete, because it's not just the signal that matters. The success of any measurement depends, we know this in physics very well, depends on the signal to noise ratio. Reducing the noise is equally useful as increasing the signal. And this is not different in healthcare. In contemporary one-size-fits-all healthcare, molecular levels, usually measured by single analyte assays, are compared with population-based reference ranges, implying biological noise dominated by the heterogeneity of controls, the variability of homeostatic values of healthy individuals. We are all different. But perhaps this biological noise can be suppressed by more advanced healthcare modality. Future preventive care calls for two revolutions: for physical technologies that, instead of measuring molecular parameters one by one, are able to access hundreds or even thousands of them reproducibly in a single measurement, and for a healthcare modality that, instead of referencing to other individuals' values, enables us to use our own previously measured value as a reference. These are the revolutions that we wish to bring about with our Protecting Health global initiative for creating the foundations of precision that is individual-based preventive care of the future. The story I'm telling you started on the turn of the new millennium, when our group at the Vienna University of Technology succeeded with attosecond flashes of light in capturing the fastest processes outside the atomic core, the motion of electrons, as exemplified here by electron migration in organic molecules. This slow motion replay is performed with a time magnification of 10 to the 15th, 1,000 trillion, actually equivalent in space to the magnifying power of the world's most powerful space telescope and electron microscope in combination. The attosecond metrology we originally developed for tracking electronic motions has also proven capable of sampling the oscillation of light waves. This solution was looking for a problem, has been looking for a problem for quite a while, and found it some 15 years later by capturing molecular vibrations in human blood in real time. Imagine we expose cell-free blood to an extremely brief infrared laser pulse, which excites a wide range of vibrational modes in the molecules. The vibrating molecules in turn emit coherent infrared light in the wake of the excitation. Just as the musician's tuning fork generates acoustic waves following a hit, whilst the sound waves radiated by the tuning fork oscillate only a few hundred to a few thousand times per second, the infrared molecular signal oscillates several 10 trillion times per second, which nevertheless can now be captured by attosecond metrology. This infrared electric field molecular fingerprint delivers hundreds of parameters of molecular origin. Unlike mass spectrometry-based proteomics, metabolomics, and lipidomics, the spectroscopic features of infrared fingerprints deliver information about groups of molecules rather than concentration levels of individual analytes. Our multimodal phenotyping approach unites all these cutting-edge technologies for acquiring unprecedented amount of molecular information, thousands of molecular parameters from human blood. Let us now consider one of the accessible molecular variables that is highly stable over time in a healthy organism. This parameter can be a spectroscopic feature affected by a group of molecules, as I just said, or it can also be a concentration level of a particular analyte. The high temporal stability implies a narrow person-specific reference range, way sharper than the spread of the variable in healthy population. If this parameter is sensitive to the development of a particular disease, it increasingly deviates from the person-specific healthy baseline, this green stripe, with progression of the disease, and may provide first indication about the unfolding disease long before symptom-guided healthcare can diagnose it. Detecting this disease before symptoms manifest requires us to donate blood repeatedly while we feel perfectly healthy, in sharp contrast to what we are doing today, to what we are doing in the existing symptom-guided healthcare. This is the price we will have to pay for protecting our health more effectively. And the price we have to pay for establishing this new healthcare modality is a new clinical study design. Repeatedly recalling individuals to establish their personalized reference range and then following them up for capturing slowly evolving chronic diseases at their early stage of development and for signaling risk of sudden events, such as stroke or a heart attack. Precision prevention relies on person-specific reference ranges, which can only be acquired by repeated measurements within a short period of time and upon frequent recalls to capture unfolding conditions at their earliest stage. We refer to the new study design meeting these requirements as a longitudinal cohort study with repeated baseline and high-frequency follow-up. Briefly, Protecting Health. The prototypical Protecting Health study was initiated by our Center for Molecular Fingerprinting in Hungary more than 5 years ago, with a target cohort size of 15,000 participants aged above 40. We have meanwhile recruited almost 13,000 subjects, from whom our team up to now collected more than 73,000 blood plasma samples. This is the first large-scale study that enables the robust evaluation of person-specific reference ranges and their evolution with healthy aging of all accessible molecular parameters of human blood, out of which we aim to find those with smallest within-person variations, highest stability over time, and strongest response to one or more prevalent NCDs. Strongest response means strongest deviation from the healthy baseline. For some 5 years, I've been showing this conceptual slide to audiences all over the world. Since early June, I can now show that this is more than just a concept. In our prototypical Protecting Health study in Hungary, first participants have been diagnosed with NCDs after they had donated blood at least 6 times before diagnosis. They have opened the door to the systematic scrutiny of the predictive power of blood plasma parameters, and obviously we first looked at infrared molecular variables. Here you see how the ratio of selected spectral amplitudes of the infrared light emanating from the plasma samples of a study participant diagnosed with thyroid disease almost 4 years after enrollment evolves over time before diagnosis. The spectroscopic variable exceeds the person's normal range 2.4 years earlier than diagnosis, most probably in a symptom-free early stage of the disease. Here, another variable's response to the development of a lung disease. The first red flag appeared here only slightly less than a year before diagnosis, but the great deviation from the normal range at this time indicates that the parameter probably might be able to signal the onset of this disease by more than 1.5 years before diagnosis, or maybe even more than that. This also suggests the need for more frequent recall than we did initially in our study in Hungary, namely once a year in the follow-up period. And indeed, meanwhile, we changed the protocol in Hungary, and after the fourfold repeat of the baseline, recall our participants twice a year, and will do so also in the other protecting health studies to be rolled out hopefully soon. Yet another variable appears to provide first indication for the increased risk of the onset of a cardiovascular condition 2 years before the actual condition was diagnosed. Last but not least, we identified also an infrared variable signaling the development of type 2 diabetes in the plasma sample sequence of a study participant 2.3 years before diagnosis, and actually before the widespread marker hemoglobin H1C could have set off alarm bells. Obviously at a stage when the disease would have been clearly reversible. These are preliminary results, first results of 7-year efforts. They reveal first candidates for pre-symptomatic biomarkers which may enable cost-effective early detection of prevalent NCDs. But candidates are not yet biomarkers. To be able to remove the question mark, we need at least several dozen, better actually several hundred, new onset cases of the same disease to render the candidates a true pre-symptomatic biomarker for the particular condition. For many severe conditions, the cohort in Hungary will not yield a sufficient number of cases, nor does it represent all ethnicities. That's why we took the initiative of expanding the project from Hungary to other countries and continents, whilst our Protecting Health Hungary study is being continued. Our Protecting Health Hong Kong study is about to start within a few weeks, hopefully with the first subjects to be enrolled in August, just a few weeks from now. And we also very much hope and work on it very hard to initiate the Protecting Health Germany study also, if not in this year, but hopefully in the first half of next year. And I'm most happy, I feel truly privileged, and I'm most happy to report that we are just about to start discussing the feasibility of a Protecting Health study on a continent where the anticipated future impact of preventive care would be by far the largest, as apparent from this burden of disease map. Indeed, Africa would benefit like no other continent from preventive care, and I'm most happy to announce that Professor John Amuasi, who initiated discussions about protecting health Africa with this very email just a few weeks ago, is here with us today and will join us for my Nobel Hour this afternoon to discuss the anticipated impact of this project for his continent and for the rest of the world. Finally, I'd like to briefly recap what we are doing and what we are aiming for. Our study participants donate blood 4 times within a few months right after their enrollment, allowing the selection of molecular variables highly stable over time, which imply the narrowest person-specific ranges. These are the primary candidates for personalized care. Over the subsequent years, the development of prevalent NCDs will up or down-regulate some of those variables, uncovering the best pre-symptomatic NCD predictors among the accessible molecular parameters. Whilst the blood sample collection is continuing, the profiling modalities will be optimized for these pre-selected markers. They will be actually optimized for sensitivity and throughput. Higher throughput means lower cost. Cost effectiveness will be extremely important to actually translate this technology and this methodology to everyday life. All these steps can be accomplished in the absence of clinically diagnosed new onset cases, while those cases accumulate over the years to eventually allow establishing causal links between outcomes and parameter changes. With these links, an algorithm for detecting prevalent NCDs in their early pre-symptomatic phase of development will be trained and validated. This way, we aim to create the first comprehensive screening platform for prevalent NCDs, which we dubbed PH 1.0. For gaining actionable health insights into the major non-communicable diseases, including cancers, cardiovascular, respiratory, metabolic, and hopefully even one day neurodegenerative disorders at the earliest stage of their development, based on the correlated and hence highly specific change of a number of early NCD predictors. No matter what future technology will be successful in capturing most cost effectively the most powerful early NCD predictors, their validation will have to rely on the blood samples and accompanying health data that we are creating in the Protecting Health endeavor. We are building the most valuable biorepository for preventive care. Thank you very much.